So that's a little bit about DAGs and how you kind of think about variables and how they relate to each other. In terms of simulation, and also thinking analytically, you have to, it's helpful to know that not all variables in your data generating process kind of need to make it to your data. So what I mean by that is you can have this situation where you have actually you can imagine that there are really four random variables that are interplaying. So z, x, and y, but also u. It's just that u is something you don't get to see in your data set. So I'll show you an example of simulating that. Let's say you had, you're imagining that what's actually happening is that the value of u, you have this variable u, like a latent variable that's affecting the variable of x. So for example, maybe x is somebody's level of education, and z is like their parents' education, and y is salary, and u is some latent factor like socioeconomic status, which you don't have the ability to measure. For in this example, obviously socioeconomic status is impacting somebody's level of education, but perhaps you don't see it. It's still useful to think about it, to imagine it if you're doing simulations, because then you can specify, okay, well, how does this thing rely on this unobserved variable? I'm just going to pretend I can see it, and then at the end of the day, I'm just going to get rid of it from my data set. So the data that I'm going to get is just these variables, x, y, and z. But to generate x, y, and z, I've depended on u. And you can do this also not just to model situations where you have something that's unobserved, but also as a way to kind of create funky distributions if you want. So for example, let's say I have I'm going to actually make 3 random variables, s, u, negative, u positive, and x. And so let's actually take this as an opportunity to do a little exercise. From this code, let's draw a DAG. So I'm starting with s. S doesn't depend on any other random variables that I've made. So I have s. Then I got this u negative. This also doesn't depend on anything else. So I'm just going to write like this. And then u positive also doesn't depend on anything else. And then all of these are going into determining this random variable x. Okay, so this is really determining a joint distribution between these 4 different random variables. But at the end, I'm just getting out the variable x. So all I'm going to see is the marginal distribution of this guy. And I've gotten rid of all the other variables. So this thing here makes a data table that has s, u plus, u minus, and x, okay? And I'm generating this, in theory, for my whole population. And then what's going to happen is I'm just going to select just this column, and what I'm plotting here is just this marginal distribution. So I'm plotting this and making the kind of like histogram of x and showing you what that looks like. And it looks kind of funky. And that's cool, because there's no way to just say x equals r, camel or something like that, some like double hump distribution, and just get it. But you can custom make ones. And the way I did it, so we can dig into this, I chose s to be a variable that's either 0 or 1. Okay, just 50% of the time it's 1, 50% of the time it's 0. I chose this u minus to be a normal distribution with mean equal to -2. So maybe we draw it like this. And then u plus to be a normal distribution with mean equal to +2. So it's like that. All right. And now x, I let that be if s equal to 1. So in the cases where I have s equal to 1, I choose this one. I choose whatever value I have for u in this row here. If it's 0, I choose whatever value I have over here. And so what I'm going to get is a kind of mixture of these two distributions, where sometimes I'm getting the value drawn from the positive normal distribution, and sometimes I'm getting the value drawn from the negative normal distribution. The other thing that I did is I said, actually multiply, when I'm taking the one from the positive one, multiply that by 2. And what that does is that, so if I have here's 0, and my distribution looks like this. and I'm multiplying it by 2, what that says is any time that I would have chosen, I would have gotten the value 1. So all of these guys are now, actually I'm getting the value 2. Anytime, so I get this little kind of peak here. Anytime I would have chosen the value 1/2, now those guys are all going to 1. So those guys are getting moved over to 1. Anytime I would have chosen the value 3/4, those guys are getting moved over to over here. So this actually increases, this kind of spreads out the distribution and moves it over. So that's why this is kind of shifted over and spread out. You can see if you get rid of this 2, you'll just get something that looks like this, okay? So this is hopefully fun. I encourage you to play with this. Just try to make weird shapes. Last thing I want to show you here is I used if-else, but you can also write this mathematically if you want to notate a kind of if-else statement. You can say like x equals 1 if, y something, right? And then else, right? That's the same as saying x is equal to 1 times this something that takes a value 1 if y equals whatever plus the value 0 in the other case, right? Or y, some indicator where y equals some other stuff. So you can write it as the sum of two terms, where each of those two terms is like the value that x takes if this thing happens times plus the value that x takes if this other thing happens, because in any case, either this thing is going to disappear or this is going to disappear, and you're just going to be left with just that value, just this value, or just this value, depending on which case you get. And if, for example, if you have, let's say, let's complicate this a little bit. So value is 2 and then minus 3. Okay, if y equals 1, if y equals 0, if you have y equals 1 and y equals 0, then this indicator of y equals 1 is just y. So this is just the value of y. Because when y is 1, it's 1. When y is 0, it's 0, right? And then this thing, I need this to be 1 when y is 0, and I need it to be 0 when y is 1. And so I can write that as 1 minus y. And so this whole thing here, and now I change these not to 1 and 0, but to 2 and then minus 3. So you can write it like this, and that's the way I have it here. It's something that if you're like reading papers or code, you can just like trip up on a lot, but this is equivalent to like an if-else, where s is being the kind of like condition variable. Okay. Another handy use of these hidden variables is to collapse multiple variables into one parameter. So in this scenario, I have x and z are things that I'm generating marginally, and then u is kind of matching them together. So here I'm saying u is 5 times x minus z, and then y is some random variable that's mean depends on u. So I could have just copy-pasted 5x minus z here, right? But maybe there's another variable, q or w or something, that also depends on this like kind of shared latent variable. And so then this would be helpful as like an intermediary. I think maybe the last trick about simulating things in R. So I've shown you can use hidden variables to create funky distributions or create like represent things that are latent, not observed in your data set. Just put them in there, right? Another handy little trick is that when you have binary variables, which we often do in health, like does somebody have a heart attack or not? But those binary random variables, there's only one distribution for binary random variables, and it's the Bernoulli distribution. The only thing you can change is what this probability is, right? Because if a variable is binary, it's only what's the probability that it's 1, what's the probability that it's 0. That's it. That determines the whole distribution. And so for the standard Bernoulli, it's 1/2, 1/2. But you could have a case where it's sorry, this should be like that. So 0.75, 0.25, which in this case would be Bern 3/4, right? So the only thing that changes is what this value in here is, the probability of that thing. So all you have to model is what is the probability of the thing happening. You have to determine what that is. Okay, when you're choosing how to simulate a binary variable. And the problem with that is that, okay, it's easy. Let's say you want your binary random variable to depend on some other continuous random variable, like somebody's age could affect their risk of heart attack. Well, if your random variable, your age, is a number between 0 and 1, okay, that's no problem. I can relate it like this. I can just say the risk of getting a heart attack is exactly somebody's age. And maybe it's something more complicated, but let's say this is a very simple example. The problem is if age is just a generic number, so here this symbol means any real number between minus infinity and infinity. In this case, it should really be a positive real number, but whatever. If age is any number, like let's say between minus 100 and 100, if I can't say the probability of y given x is a coin flip with a probability equal to 100, because probability is only a number between 0 and 1. And so this doesn't work. And so you often need some way of squishing down these numbers to get something that's between 0 and 1, to translate something that can be between minus infinity and infinity to something that's between 0 and 1. And by far the most common choice that people use is the logistic function. It's also called the sigmoid function. And it's just this S shape here. So if you make a plot of it, so what you put in a value x, which is any number. And what you get out is a number between 0 and 1. So more extreme negative values of x correspond to values closer to 0. And large positive values of x correspond to values close to 1. So this is a very common way that people basically squish numbers down into a probability. So here, if x represented age, or in this case it's somewhere between minus 100 and 100, whatever that might be, I can say y, the y is a coin flip where the probability of getting heads is the logistic function of x. So if x is a very big number, like 100, we have very high chance of getting heads. If x is a very small number, like minus 100, it's a much smaller chance of getting heads. If x is 0, that corresponds to 50-50. So by doing that, you can come up with kind of like linear or any function of x you want to determine what this kind of value here, which by the way will end up, I think we'll see later, corresponds to the log odds of the probability. So you can just determine what the log odds is. That's any function you want, and then just squish that down to be between 0 and 1. So that's the last trick for doing simulations.